So this is a really useful property with Laplace transforms called the shifting property. And so what it tells us is that if we take the Laplace transform of an exponential function e to the at times the function little f of t, its Laplace transform is capital F, which is the Laplace transform of little f, evaluated at s minus a. This is called shifting because you're shifting the argument by a, and the a comes from the power of the exponential function. So let's just take a look at a few of the examples here. I think you'll find it fairly simple to apply. So let's say we want to find the Laplace transform of e to the 2t times the function sine of 4t. So in terms of this property as it's listed, the little f of t function is sine of 4t, and here's your exponential function. So here your a is 2. So what does this tell us? Well, let's look at the Laplace transform of little f of t, the sine of 4t. Well, our formulas tell us that the Laplace transform of the sine of kt is k over s squared plus k squared. So the Laplace transform of the sine of 4t is 4 over s squared plus 4 squared. So what does this tell us with the shifting? It tells us to replace that s with s minus a. So every place we see an s, we're just going to replace it with s minus a. So we get 4 over the quantity s minus 2 squared, because a is 2 in this case, plus 16 because 4 squared is 16. So that's how you do it. So just look at the Laplace transform of little f, find out that formula, and then apply the shifting to that variable s by the amount s minus a. Let's look at this one. The Laplace transform of e to the 3t times cosine 2t. Now, here's our formula for the Laplace transform of the cosine of kt. And remember, you probably will start remembering these, but we can always look at our table. It's given by s over s squared plus k squared. So for the cosine, you have an s in the numerator. For the sine, you have the constant. So every place we see the s, we have to shift that s by make it s minus a, or in this case a is 3. So every place we see the s, we will replace it with s minus 3, or s minus a. So we have an s in the numerator, so that becomes s minus 3 because a is 3. And again, s minus 3 in the denominator. And this time our k is 2 because we have cosine 2t. So simplifying it, we just get s minus 3. We don't really need the parentheses in the numerator, over s minus 3 squared plus 4. So you might wonder now, why does this work? Some students really like to know why things work. So this is a little proof. So let's say I was taking the Laplace transform of e to the at times f of t. So by definition, it's defined as e to the minus st, this improper integral from 0 to infinity, e to the minus st times our function. This is our function. So what happens here? We can take these two exponential functions and add their exponents. That's all we're doing here. And we're just going to factor out a minus t. So that's what we get. So when you look at that, the improper integral from 0 to infinity, e to the minus s minus a, this is the definition of the Laplace transform, but in the place of s, this expression here, s minus a, is replacing the s in your Laplace transform. So that's all that means. So that's all the shifting property means. So it's just a simple little calculation with an integral. All right, let's do a few more examples. So what if that power there is negative? So here we have the Laplace transform of e to the negative 4t times the sine of t. So if you take the Laplace transform of little f of t, you just get 1 over s squared plus 1 squared, which is 1 over s squared plus 1. Now what's our a? This time a is negative 4. So every place you see an s, you're going to replace it with s minus a. Well, this time you have s minus a negative number. So that becomes s plus 4 squared plus 1. So anytime you see s plus 4 or s plus a, that means you have a negative power with the exponential function. Now, here's another interesting property, and really the only reason we use this property, really for what we're going to do, is to figure out the Laplace transform of powers of t. So take a look at this note I've written to you. That's why we're learning it. We're not going to be using this property very much other than to do what we're about to do. So don't worry about it. So if we have the Laplace transform of t raised to a power, let's say that's an integer power times a function little f of t, it's defined as -1 to the nth power times the nth derivative of f of s, where f of s is the Laplace transform of little f. So let's just see how this works. So let's say I want to find the Laplace transform of t. Now this is a way of finding the Laplace transform of t without using the definition. If you use the definition, think about that. You'd have t times e to the minus st. You'd have to integrate by parts. So every step of this problem, we'd be integrating by parts more and more times. As we raised, we'd have to, if we had a t to the nth power, we'd integrate by parts n times. So it get kind of complicated. So we're trying to find an easier way to do it. So let's look at the Laplace transform of t. That's the same thing as the Laplace transform of t to the first power times 1. So if we're looking at this formula up here, our n is 1, little f of t is 1. So both n is 1 and little f of t is 1. Now what is the Laplace transform of little f of t? If little f of t is 1, it's just 1 over s. So this formula tells us the Laplace transform of t, which is the same as t times 1, is -1 to the first power times the derivative of f of s. But the Laplace transform is just 1 over s. We plug that in. -1 to the first power is -1. Now, to differentiate 1 over s, write it as s to the -1. We get -1. This derivative would be -1 times s to the -2. Multiply these together, you get 1 over s squared, just moving the -2 power to the denominator. So the Laplace transform of t is 1 over s squared. We'll do it one more time. What if I want to take the Laplace transform of t squared? So here, in this terms of our formula, n is 2. So this is the same thing as Laplace transform of t squared times 1. So f of s again is 1 over s. Our formula says Laplace transform of t squared, our n is 2. We'd have -1 squared. We'd have to multiply by the second derivative of 1 over s. Well, we know the first derivative is minus s to the -2. We did that right up here. What's the derivative of minus s to the -2? We'd have a -2 times -1, which is 2, times s to the -3. That's what we get. Then that's just rewritten as 2 over s squared. So the Laplace transform of t squared is 2 over s cubed. So are you noticing a pattern? That had a first power, the denominator had s squared. This has a second power, the denominator is s cubed. Had a 2 in the numerator here, had a 1 in the numerator there. Are you seeing a pattern? And that's really how we use this property. So here's the pattern. We started out with t, we got 1 over s squared. T squared, we got 2 over s cubed. If we kept taking those derivatives, as the property told us to do, if we differentiate it again, we get a 3 times 2 over s to the 4th. If we differentiate it again, we have a 4 times 3 times 2 over s to the 5th. So do you see what happens here? I don't know if you're familiar with factorials, but this is 2 times 1. This is 3 times 2 times 1. This is 4 times 3 times 2 times 1. So in general, if you're taking the Laplace transform of t to the nth power, it's given by n factorial, so whatever the power of t is, n factorial over s to the n plus 1 power. So you don't have to do that property, we just have the formula. And it's in that table of Laplace transforms that we have in the book and that I have in folio. So for example, if you had the Laplace transform of t to the 5th power, it's defined, so our n is 5 factorial over s to the 5 plus 1. So that's 5 factorial over s to the 6th power. 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. So that's the Laplace transform of t to the 5th. Now, you can use this in connection with the shifting property. So what if I said, hey, what's the Laplace transform of t to the 5th times e to the 2t? Well, we're shifting, we're multiplying this function, that's our little f of t, times the exponential. So every place we see the s, our a here is 2. We just shift the s by s minus a. So we replace this s with s minus 2. That's all you have to do. So that's what I'm saying here. Laplace transform of t to the 5th is 120 over s to the 6th. Just shift that argument with s minus a, where our a is 2. So these powers of t are really simple. You use this formula, and then if you multiply by an exponential, just use your shifting property. And one last example. Let's say I have t cubed times e to the negative 2t. Now, we're going to use shifting again because we're multiplying by an exponential function. Laplace transform of t to the 3rd power is 3 factorial over s to the 3 plus 1. This is 3 times 2 times 1, which is 6, over s to the 4th. We're shifting. We have an e to the minus 2t, so our a is negative 2. So we replace our s with s minus a, but our a is negative. So s minus negative 2 is s plus 2. So we end up with 6 over s plus 2 to the 4th.